Well, hey everybody, Mr. Black here. Hope you're doing well. This is our first astronomy lesson for the fourth quarter. It's linked to a slide set called the Life Cycle of Stars. I converted it from a PowerPoint to a PDF, so it'll be linked to the Google Classroom. And you know, with these first few slides, we could stay on these forever, but there's some few common things. All stars start with a nebula, a gas cloud. Could be just hydrogen and helium from the Big Bang, or could be seeded with heavier elements from old dead stars or a supernova explosion. But what happens is it starts to condense, it starts to get thicker, it starts to heat up, kinetic energy increases, and then the beginning of nuclear fusion begins a stage called the protostar. Proto means in the beginning, you get a star. And this, all stars do that. They start from a nebula, go to protostar. Then they go into what's called the main sequence. That's the main hydrogen to helium fusion, part of a stellar life. And this is where size matters. It's all about mass. Okay, there's the low mass stars like our sun. There's what are called massive stars, or about 4 to 20 times the mass of our sun. And then there's the supermassive stars. Those are 20 times and greater. Stars such as Betelgeuse and Deneb, stars we know about. And that determines their ultimate life cycle. Okay. If you look at that first slide, depending on size, it can go red giant, supermassive, or red supergiant. But then the low mass stars like our sun form a planetary nebula. That's basically a dead, dying, decaying star. And then what's left is that white dwarf core. It's really hot, really small. The average size of a white dwarf is about the size of Oregon, about 250 to 300 miles in diameter. Really hot, but very dim because they're so small. There's not a lot of surface area. Now the massive or supermassive stars will go supernova. We've mentioned that a little bit with Betelgeuse. Once they go supernova, they blow themselves to pieces, but in that supernova, that explosion, boom, causes an implosion. For every action, there's an equal and opposite reaction. And you can form what's called a neutron star, just like the name sounds, pure neutrons. Or you can form the black hole. It can be so dense that it rips through the space-time fabric and becomes the end point of a supermassive star, and we'll talk more about that later. Same thing, these stellar evolution slides you can see the common thing. There are also the really super low mass stars. Those are called red dwarf stars. Those are so dim and hard to find. It took infrared telescopes, one called the WISE, the Wide Infrared Space Camera, to actually start finding these. Those are very interesting, and we'll kind of finish this talk with those. So notice, no matter what you find on the internet or in your textbook or in the notes, you basically end up with three things: a white dwarf, a neutron star. Those are also called pulsars, but we'll talk about that a little bit later. Now, turning off my phone, somebody's calling me. Now back to this. Notice here in this third slide, we introduce what's called the brown dwarf. That's a protostar or a nebula that condenses but doesn't have enough gravity, doesn't have enough mass, doesn't have enough heat, particle motions to actually begin fusion. That's actually like Jupiter. Jupiter actually is lives in two worlds: a supermassive planet, the largest planet in the solar system, and a failed star called a brown dwarf. You'll see that pathway in the third slide. Like I said, these are all kind of the same thing, just with differing amounts of detail with the same three results. Interesting enough, when we get to the fifth slide, we start seeing how we tie astronomy and chemistry together. Notice in this source of elements, the Big Bang is only accountable for forming the hydrogen and helium. Now all the green are larger stars. We see that mostly goes up to iron and atomic number 26. Some really massive stars like Deneb and Rigel, Betelgeuse can form heavier elements. But once they begin to form iron, which is atomic number 26, that's when things get dicey. They're too hot, they're too dense, they can't fuse heavier elements stably, and that's when they're the end of their life or the supernova event's close to happening. That's where we are with Betelgeuse. Hopefully you're still out there with me, hoping that Betelgeuse goes supernova one of these nights. It'd be great if it did it in the winter when we could see it at night. If it happens during the summer, we'll actually see it during the day, which won't be as dramatic. It'll still be great, but not as great. Notice the supernova, everything in the kind of that peach salmon color. Those elements can only be formed from the heat and pressure of a supernova. So we can see how important stellar evolution is in producing the stars of the periodic, or the elements of the periodic table. Let's get to 6. This is close to home. This is our sun. You can see where we are. I don't have to tell you we're about 4.5 billion years into our hydrogen source. Our sun is gradually going to go into red giant when it runs out of hydrogen. And then once carbon is formed in the core, it's going to go planetary nebula and then be left with a white dwarf. The elements produced will seed another nebula, and new stars can be formed from the elements our sun makes. So this is a cycle. This is something that goes on. It's a life cycle of stars, even though no one thinks stars are actually alive like you and I. If we look into the cross-section of a star, you can see that the temperatures are hotter towards the core, and that's where the heavier elements are formed. Like I said before, once you get to iron, that's when a star is beginning to end its life cycle and getting ready to go supernova. I put in a shot of the Hubble Space Telescope. If you've ridden in a cheese wagon lately, you know the size of the Hubble Space Telescope, about the size of a 44-passenger school bus. It's where a lot of these, I'm going to kind of go through what we see in the life cycle, the different stages. We could do this with anything, and this we're going to do it with stars. But Hubble is where, of course, there have been over 100,000 papers published off data from the Hubble. So we have to always, thank our instruments and our tools to come up with the conclusions that we know. Here's, of course, a nebula, a star-forming region. This is M42 in Orion. If you have a telescope or binoculars, get out and look in the sword of Orion and see this. This is where 440 stars are currently condensing in that nebula. It's a very thick region. And of course, in the belt of Orion, near the star Alni's Tack, you've got the Horsehead Nebulae, another area where hydrogen and heavier elements are condensing to form that protostar. As mentioned, there's the protostar, and you can see that all this material is moving, condensing. We know a torus structure, a spiral is a very common structure in our universe. Gravity's pulling everything in and causing it to spin. It's got a lot of angular momentum. You can see that in slide 11. Once the star begins to fuse, the solar wind that it would produce will kind of kick out a lot of the lighter elements, push them out to the outer reaches of the solar system. And that's where you have stuff like the Oort cloud, all the hydrogen and the oxygen, forming water out on the edges of these solar systems. I'm sorry to bring this up, but we didn't get to take the final from the third quarter over comets, asteroids, and meteors. So we'll give everybody a pass on that one. Here's a artist's rendition. We've actually seen pictures of similar things like this. One famous one is in Eridanus. There's a solar system forming right before our very eyes, where you see lots of asteroids, comets. You see little areas outside the star where planets are forming. Gravity doesn't take breaks. Think about that. It doesn't matter what time of day or night you fall off a ladder. Matter is drawing in other matter, just like the Earth draws you in when you fall down. This is interesting. Look at slide 13. In 2003, early in my astronomy teaching career, the IRAS, which is an infrared space telescope, found the moment of creation. This is a protostar in Taurus, a new star. So when we look at the stars in the planetarium, there's actually a new star that's not shown. That's in the kind of the front leg of Taurus, the bull. So stars do form and stars do die. We're waiting for Betelgeuse to end its life at some point. So there it is, the moment of stellar formation right there, the protostar in Taurus. Now the main sequence is kind of that adulthood that all stars go through. The main sequence. Stars either start out as blue supergiants or blue giants or white stars if they're low mass. And then they start kind of turning yellowish orange as they begin to age. And this, of course, is our sun here. It's at the main sequence where the most common fusion product, and make sure you remember this, a main sequence star, the most common fusion product is hydrogen fusing into helium. So keep all that in mind. Ooh, Betelgeuse. Now, if we put a spectroscope on this, we'll see that Betelgeuse is emitting iron light. We know spectroscopes can pick out the elemental composition of a radiating hot body. That's obviously what a star is. This has got iron in its core. We know that's an unstable configuration for a star, so we know it's going to go supernova. Since it's larger than 20 times the mass of our sun, we know that the final product of that supernova will be a black hole. So stay tuned. There's about to be another black hole in our solar system. Now look at that. Slide 16 is what are considered the most beautiful things in the universe. These are the planetary nebulae. These are stars, low mass stars like our sun, 1 to 4x, that have just run out of fuel. There's no more hydrogen or helium to fuse. They fall apart. And if you look into the center of all these planetary nebula, there's a little white dwarf. All the different colors that you see are the different elements produced, all the way up to, in some cases, silicon for some of these. But these are considered absolutely beautiful, and they're part of the life cycle of a low mass star like our sun. So you're looking at the future of our sun in this picture, in these pictures. Here's the Ring Nebula. This is in Lyra, the summer constellation, and look right in the center. You see that white dwarf. That's that little pure carbon. And by the way, through resonance studies, we know that pure carbon center is, drum roll, diamond. Yeah, got your attention, right? So we've got a diamond the size of Oregon inside of this. We can see all the nitrogen and oxygen and the helium and all the different lower mass sulfurs, lower mass elements, phosphorus, that were created in this star. These planetary nebulae are beautiful. Here's a white dwarf. These don't put out a lot of light, so the images always come up pixelated. They're very dim because they're so small. They're very hot. White is hot. When we get to the Hertzsprung-Russell diagram or the HR diagram, these white dwarfs don't put out a lot of light, but they do put out a lot of heat. If you went to it, it'd be really hot. Guess who's got a white dwarf companion, and that's Sirius, the brightest star in our sky. You can see it in this image orbiting around it. Now what these can do, these little white dwarfs, they can draw the outer gases from a neighboring star, and they can produce a type of supernova. It's kind of rare, but that's when a white dwarf feeds off, and then it explodes from getting that white carbon dwarf too hot. Those are rare, but they do happen. Those are the type 1A supernovae. Look at this. This slide, it doesn't appear to be numbered. but this is a picture by a North Medford kid, Cody Salerno. Took a picture out in the observatory of Sirius, and then look at the bottom. See the little white dwarf orbiting really close? That's a candidate for being one of those sneaky little supernovas, not where a star blows up, but where a white dwarf begins to steal hydrogen and helium from a neighbor binary star pair. Good job, Cody. Look at this comparison between Deneb and the sun. Being 20x the sun, we know it's going to go supernova and then, of course, become a black hole. So Deneb, which you remember, Deneb's in the constellation, yep, you're right, Cygnus. Cygnus is Swan. If you stay up after midnight, you can go out and see that on a clear night. And this is supposed to be a double burst. This doesn't work in PDF. Trust me, a supernova has an implosion. That's where the heat from the nuclear fusion runs out, causing all the outer gases to implode. Then they hit that hot iron core and explode, and that's game over. That energy explodes out into space. Here's the moment of an explosion. This is Zeta Carinae, the southern hemisphere. Here's a star that just blew itself to pieces there. Here's another explosion. This is the Crab Nebula. This is in M1, which is in the horns of Taurus. There used to be a big red giant 1,000 years ago, which blew itself to smithereens. We do expect a supernova about every 100 years, so we're ready for one. This is a moment of creation. This is where the elements, especially the heavier elements, are created. Here's a nice Hubble shot of the Crab Nebula, Supernova Remnants. There's the Veil Nebula. There's lots of examples of those for you to see. And that energy is expanding out into space as we speak. Now for the massive stars that are between 4 and 19x, we have what's called a pulsar. A pulsar is a neutron star, so that implosion, instead of blowing the core apart, it actually compresses it. All chemistry stops. Everything is neutral charged. Without those charges, they pack it really tight. Neutrons are the densest thing we know in our world. And these, the explosion causes them to spin. And if you get neutrons to spin rapidly, you get a strong pulse of radio. So we pick up the pulsars and radio waves. They were first found in 1967 by accident. We found these pulsing radio stars, and I'll link some of those on the Google Classroom at some point. Here's radio waves pulsing out of the Crab Nebula. That's that star that blew itself up in 1054. And then here, once we get a black hole, it was really hard to prove that black holes existed. There's going to be a lot more information on black holes coming up. But black holes, they're so dense, there's so much matter crushed in such a small place that if they get in front of a light source, according to Einstein, they will lens or bend the light and focus it. We know when we focus light and make things brighter, it's because we bend them in the, we know that can actually happen with a black hole. And you can see this is the very first proving of a black hole drifted in front of a star. Now this is a non-feeding black hole. There'll be a difference. Now in our galaxy, if there's a supermassive star that blows up once every 100 years, that means our Milky Way's got about 30 million black holes in it. May seem like a lot, but if you think about the fact that there's probably 400 billion stars, 30 million is not that much. Here's how you actually see a black hole. When it feeds, the material falls into what's called the event horizon, and we'll detail this more in a future lesson. The material is accelerated to the speed of light. That's the definition of a black hole. Things fall in at the speed of light, turning the matter into energy. That energy is seen in radio, it's seen in X-rays, and it's seen in visible light. And look at these images on slide 30. You see what are called the jets. The jets are the energy that aren't consumed by the black hole, emanating out into space. Here's the Shanda X-ray telescope. It sees in X-rays, and black holes give themselves away in X-rays. This is several black holes orbiting around the Milky Way, the center of our galaxy. If you go out in the summer and look at Sagittarius, you're actually looking into what is our black hole, which is currently eating a few million uh, stars. It's going to eat them all. It's just a matter of time. We'll talk about that more later. Look at all these X-ray sources in the Andromeda Galaxy. These are all black holes that are orbiting around. You can see visible light to the right and X-ray to the left. Turns out black holes are very common. Interestingly enough, black holes were just dreamed up and theorized back during the time of Einstein and Schwarzschild in about 1916, and they weren't even verified until 1987. This is it's an animation that should show you the center of the feeding black hole in the middle of the Milky Way, but it doesn't go in PDF. This is interesting enough that Hubble in 2001 verified a black hole in a distant galaxy called Centaurus A, and a North Medford student, Molly Woodard, did a remote control of a telescope down in Australia to view it. Look right in the center. You can see this very complicated galaxy. Here's a Hubble shot. Hubble's a little bit better than the 20-inch telescope she was using. But in the center of that, you actually can see there's the Milky Way, and these are the jets, the undigested energy and X-ray, invisible light, and radio waves, material blasting out 90 degrees to the event horizon. So the paradox of a black hole is that they're very bright only because the matter is being accelerated to the speed of light and putting out lots of energy. This was the black hole video from the Hubble. It's not going to feed for us. This is interesting. This is the Sombrero Galaxy. This is an ancient galaxy. It's been around for billions of years, and it's eaten 1 billion stars. Look at that. Anytime you see a bulge at the center of a galaxy, that's a supermassive, not a small black hole, but a large one. And we'll talk more about that in a future lesson. There's another one. See that bulge right in the middle? That's characteristic of a feeding black hole. Here's those jets. We see them in X-ray, we see them in radio, and we see them in visible light. All the same black hole. That's M87. And it was the very first black hole verified. And here's a secret. The first black hole verified in 1987 was verified by a team including a guy by the name of Dr. Richard Chambers. And guess what? His granddaughters all went to North Medford High School. He's been a guest speaker at North Medford High School. And he, in 1987, used the Keck telescope to watch a star disappearing into the black hole at the center of M87. This is part of his original research. This is a massive, massive, massive black hole. It's the biggest one near us. But don't worry, it's hundreds of light years away. Actually, hundreds of millions of light years away. Here's some equations that we'll be doing later. This is if anything was crushed down. Schwarzschild radius is the radius of the event horizon. We could crush the Earth down if we could, get enough power like a supernova. The Earth would only be less than 1 centimeter in diameter. Isn't that amazing? Our sun would only be 2.9 kilometers, which is, not much more than little under 2 miles. And then M87, it's huge. That one's 9 billion kilometers in size. That's the one Dr. Chambers. This is from his original research in 1987. We'll worry about the math in another week or so. This is just a reminder of size. Slide 44. The sun's about 1/2 of a degree, or 32 arc minutes, or 1900 arc seconds. There's 3 different ways to measure things. And this is, we're going to talk next about how we figure out distances to things. And it's by doing some geometry and trig based on the shifting of stars. It's called parallax. And I've introduced that to you earlier. We'll talk more about it later. As promised, here's your Hertzsprung-Russell diagram. These are, anything at the top is bright, anything to the right is cool relatively, anything over here is hot. So these are the blue giants. As they run out of fuel, they get cooler and dimmer, but then some of them, of course, become supergiants and become supernova. We'll introduce this later, but this was discovered, this relationship between brightness, luminosity, and temperature was discovered by two Harvard professors, Hertzsprung and Russell. Most astronomers just call it the HR diagram to save time and effort. You know, the old acronym game. Here's the Hertzsprung-Russell diagram. You'll see references to it everywhere. We'll go into it more in depth later. I just want to introduce it. Every star is on this Hertzsprung-Russell diagram somewhere, depending on temperature, brightness, and color. Here's our sun. Luckily, low-mass stars last for billions of years. High-mass stars only last for hundreds of millions of years. And then the supermassive stars like Deneb are only going to last tens of millions. So you live around a really nice star. Then the new kind of star, we just started teaching these the last few years, of the red dwarfs. They're very low mass, they're very dim, they're very cool, and they're everywhere. We didn't know about them because we didn't know to look at them. They don't put out a lot of visible light. They're very low mass. They don't last for billions of years. They last for trillions of years. We think life could live around them, even though any planet around them would probably be tidally locked, meaning one side would face the red dwarf and one face would not. But if you lived on that twilight, right on the edge of sunrise or sunset, maybe you could eke out a living around one of them. Believe it or not, we've got one really close to us, about 4.3 light years away, and it's got planets around it, exoplanets. So there's a lot of talk with the Starshot program of sending little Arduino type computers to them to see if there's conditions for life are good. Well, we're interested in red dwarfs because they live for so long. They do put out enough heat to make a Goldilocks zone where you could have liquid water. Kind of the new, a new branch of astronomy is studying these red dwarfs. Here's some reasons why we're not sure they would work. There's not a lot of ultraviolet. Most of the light is in infrared. If UV is important, maybe that would keep life from developing. Not too sure. This is all real recent. We know there's plenty of exoplanets. We've studied that. And there's some around red dwarfs, so they're the latest thing. Well, last thing I want to talk about here in this little episode is the James Webb Space Telescope. It's been delayed over 12 years, but once it goes on, it's going to look in infrared. We'll be able to see back towards close to the beginning of the universe and the Big Bang. And we'll also be able to look at these red dwarf stars to see if maybe there are more planets than we thought. So there's the size of it there down at the Jet Propulsion Laboratory. It is huge, right? Look at it compared to, it's 3 times the size of Hubble, and the Hubble's bigger than I am, so quite a telescope. And it's going to be out there beyond the moon. It can get really dark and cold out there, which is conducive to good deep space imagery. And it's a free gravity ride. The L2, the Lagrangian point 2, is a good spot to be in. So with that, I'll leave you with hang 10 and hang loose, and look through these slides. I'm going to post them on the Google Classroom. And that's going to about do it. So adios, amigos.